In this video, we discuss how a nonlinear static stress study can be used to evaluate the nonlinear response of an overloaded steel support beam. Here we see the displacement of the beam. The deformed shape has been exaggerated to make it easier to see. However, by default, nonlinear study results are rendered using the actual deformed shape. Let's review what's required to set up and run this study. The first step is to enter the simulation workspace and create a nonlinear static stress study. We can click this icon to see and adjust the study settings. As opposed to linear static stress studies, nonlinear studies are computed over several increments. This allows us to capture geometric and material nonlinearities. In this case, we'll use 60 increments. We'll also specify an absolute mesh size of 7 mm for the study. The CAD model material was defined as generic steel, which is a linear material. We can choose a nonlinear simulation material from the Fusion 360 Nonlinear Materials library, specifically high-strength low-alloy steel. Let's look at the nonlinear material properties. The simulation material is shown in the Document Materials list. The nonlinear data is located in the Advanced Properties section of the Physical tab. The material type is plastic, and the properties are defined by discrete stress-strain points in this data table. Nonlinear static stress studies are able to update the stiffness of the material throughout a simulation. Click this icon to see a 2D graph of the stress-strain curve. Slightly nonlinear behavior begins at about 230 megapascals, and nonlinearity becomes pronounced above 350 megapascals. Note that you can create your own custom materials to augment the ones listed in the predefined library. Choose an existing nonlinear material to use as a template. Then, click this icon to copy the material to your favorites library and open the properties for editing. Consult the Fusion 360 help for more information. The next step is to constrain the support beam. Apply a fixed constraint to this small face at the plus X end of the beam. Also, apply a constraint against movement in the Y and Z directions to the small face at the opposite end of the beam. These two constraints allow the beam to bend under the applied load and to float axially at the minus X end support as it bends. This setup represents an essentially simply supported beam configuration. Apply a 300 kN force acting normal to the top of the beam. Confine the force to the central portion only. The top face of the beam was split in the CAD model for this purpose. We can now solve the study. When the solution is finished, and the results downloaded from the cloud, the safety factors at the last calculation step appear. Notice the low minimum safety factor, well below 1, and how much of the beam is red. A significant portion of the beam's volume has surpassed the yield stress, but it has not yet collapsed. Since we applied a 300 kN force and specified 60 steps, the load ramps up at a rate of 5 kN per step. The maximum von Mises stress at the end of the simulation is well over the initial yield stress of 234 megapascals. It is also significantly greater than the basic yield strength of 350 megapascals. The basic yield is the stress at which the material's stiffness is offset 0.2% from the Young's modulus. Finally, let's look at the displacements. The maximum displacement occurs near the midspan and at the top flange where the load is applied. The 2D graph of this result is particularly interesting. Notice how the displacement begins to increase exponentially beyond about the 35th step. Near the end of the simulation, the slope of the curve has become quite steep, and the beam is clearly on the verge of collapse. Thank you for watching.